Now let's look into gas refrigeration cycles. As explained earlier, the Carnot cycle, the standard of comparison for power cycles, and the reverse Carnot cycle, the standard of comparison for refrigeration cycles, are identical except that the reverse Carnot cycle operates in the reverse direction. This suggests that the power cycles discussed earlier can be used as refrigeration cycles by simply reversing them. In fact, the vapor compression refrigeration cycle is essentially a modified Rankine cycle operating in reverse. Another example is the reversed Stirling cycle, which is the cycle on which Stirling refrigerators operate. In this section, we will discuss the reversed Brayton cycle, better known as the gas refrigeration cycle. Consider the gas refrigeration cycle shown in figure 1118 here. The surroundings are at a temperature T0 and the refrigerated space is to be maintained at T sub L, TL. The gas is compressed during process 1 to 2. The high pressure, high temperature gas at stage 2 is then cooled at constant pressure to T0 by rejecting heat to the surroundings. This is followed by an expansion process in a turbine during which the gas temperature drops to T4. Finally, the cool gas absorbs heat from the refrigerated space until its temperature rises to T1. All the processes described are internally reversible and the cycle executed is the ideal gas refrigeration cycle. In actual gas refrigeration cycles, the compression and expansion process deviate from the isentropic ones and T3 is higher than T0 unless the heat exchanger is infinitely large. On a TS diagram, the area under the process curve 4.1 represents the heat removed from the refrigerated space and the enclosed area of 1 to 2, 3 to 4, 1 represents the net work output. I'm repeating that the enclosed area between points 1, 2, 3, 4 and 1 represents the network input. The ratio of these areas is the coefficient of performance for the cycle and it could be represented by coefficient of performance of refrigeration is going to be equal to Q sub L divided by the network in and that also is going to be equal to Q sub L divided by the work input into the compressor minus the work output by the turbine. Note that the Q sub L is going to be equal to H1 minus H4 and the work output by the turbine is going to be equal to H3 minus H4 and the work input to the compressor is going to be H2 minus H1. The gas refrigeration cycle deviates from the reverse Carnot cycle because the heat transfer processes are not isothermal. In fact, the gas temperature varies considerably during the heat transfer process. Consequently, the gas refrigeration cycles have lower coefficient of performance values relative to the vapor compression refrigeration cycles or the reverse Carnot cycle. This is also evident from the TS diagram shown here. The reverse Carnot cycle consumes a fraction of net work, which is the rectangular area 1A3B, but produces a greater amount of refrigeration, which is the triangular area under B1. Despite their relatively low coefficient of performance values, the gas refrigeration cycles have two desirable characteristics. They involve simple, lighter components which make them suitable for aircraft cooling, and they can incorporate regeneration, which makes them suitable for liquefaction of gases and cryogenic applications. An open cycle aircraft cooling system is shown here in figure 11-20. Atmospheric air is compressed by a compressor, cooled by the surrounding air, and expanded in a turbine. The cool air leaving the turbine is then directly routed to the cabin. The regenerative gas cycle is shown in this figure. The regenerative cooling is achieved by inserting a counterflow heat exchanger into the cycle. Without regeneration, the lowest turbine inlet temperature is T0. The temperature of the surroundings or any other cooling medium. With regeneration, the high pressure gas is further cooled to T4 before expanding in the turbine. Lowering the turbine inlet temperature automatically lowers the turbine exit temperature, which is the minimum temperature in the cycle. Extremely low temperatures can be achieved by repeating this process. Now let's look at the last system in this series, which is the absorption refrigeration systems. Another form of refrigeration that becomes economically attractive when there is a source of inexpensive thermal energy at a temperature of 100 to 200 degrees C is absorption refrigeration. Some examples of inexpensive thermal energy sources include geothermal energy, solar energy, and waste heat from cogeneration or process steam plants, and even natural gas when it is available at a relatively low price. As the name implies, absorption refrigeration systems involve the absorption of a refrigerant by a transport medium. The most widely used absorption refrigeration system is the ammonia water system, where ammonia serves as the refrigerant and water as the transport medium. Other absorption refrigeration systems include water lithium bromide and water lithium chloride systems, where water serves as the refrigerant. The latter two systems are limited to applications such as air conditioning, where the minimum temperature is above the freezing point of water. To understand the basic principles involved in absorption refrigeration, we examine the ammonia water system that is shown in this figure. You will notice from the figure that this system looks very much like the vapor compression system, except that the compressor has been replaced by a complex absorption mechanism consisting of an absorber, a pump, a generator, and a regenerator, also a valve and a rectifier. Once the pressure of ammonia is raised by the components in the box, it is cooled and condensed in the condenser by rejecting heat to the surroundings, is throttled to the evaporator pressure, and absorbs heat from the refrigerated space as it flows through the evaporator. So there is nothing new here. Well, except what you see in this box. So here is what happens in the box. Ammonia vapor leaves the evaporator and enters the absorber, where it dissolves and reacts with water to form ammonia water. This is an exothermal reaction. Thus, heat is released during this process. The amount of ammonia that can be dissolved in water is inversely proportional to the temperature. Therefore, it is necessary to cool the absorber to keep the temperature as low as possible and thus to maximize the amount of ammonia dissolved in water. The liquid ammonia plus water solution, which is rich in ammonia, is then pumped to the generator. Heat is transferred to the solution from a source to vaporize some of the solution. The vapor, which is rich in ammonia, passes through a rectifier which separates the water and returns to the generator. The high pressure pure ammonia vapor then continues its journey through the rest of the cycle. The hot ammonia water solution, which is weak in ammonia, then passes through a regenerator where it transfers some heat to the rich solution leaving the pump and is throttled to the absorber pressure. Compared with vapor compression systems, absorption refrigeration systems have one major advantage. A liquid is compressed instead of a vapor. The steady flow work is proportional to the specific volume and thus the work input for absorption refrigeration systems is very small. This work input is so small that it is often neglected in the cycle analysis. The operation of these systems is based on heat transfer from an external source. Therefore, absorption refrigeration systems are often classified as heat-driven systems. The absorption refrigeration systems are much more expensive than the vapor compression refrigeration systems. They are more complex and occupy more space. They are much less efficient, thus requiring much larger cooling towers to reject waste heat, and they are more difficult to service since they are less common. Therefore, absorption refrigeration systems should be considered only when the unit cost of thermal energy is low and is projected to remain low relative to electricity. Absorption refrigeration systems are primarily used in large commercial and industrial installations. The coefficient of performance of absorption refrigeration systems is defined as desired output divided by desired input, which would equate to QL divided by Qgen plus the work input into the pump, which would be equal approximately to QL divided by Qgen. The maximum coefficient of performance value of an absorption refrigeration system is determined by assuming that the entire cycle is totally reversible. That is, the cycle involves no irreversibilities and any heat transfer is through a differential temperature difference. The refrigeration system would be reversible if the heat from the source, which is Qgen, were transferred to a Carnot heat engine, and the work output of this heat engine, which is the atothermal reversible Qgen, is supplied to a Carnot refrigerator to remove heat from the refrigerated space. Note all the equations that are associated with the work W Q sub L and the overall coefficient of performance of an absorption refrigeration system under reversible conditions, which is given as COP sub R EV comma absorption, where those values are given in terms of T sub L, T naught and Ts, and these values TL, T naught and Ts are thermodynamic temperatures of refrigerated space, the environment and the heat source respectively. Any absorption refrigeration system that receives heat from a source at Ts and removes heat from the refrigerated space at TL while operating in an environment at TO TO, has a lower coefficient of performance than the one determined earlier from the equation that is given at the bottom here. And as an example, when the source is at, for example, 120 degrees C, the refrigerated space is at negative 10 degrees C, and the environment is at, for example, 25 degrees C, the maximum COP that the system can have is 1.8. The COP of the actual absorption refrigeration systems is usually less than 1. Air conditioning systems based on absorption refrigeration called absorption chillers perform best when the heat source can supply heat at a high temperature with little temperature drop.